All right, in this lesson, we'll talk about something called a Maclaurin Polynomial. And the goal here is to make a polynomial P that'll match this function. So, and we also want to have it starting at or matching exactly when x equals 0. So the polynomial, we want it to curve and ideally match this exactly. It won't match this exactly. But here's the strategy that we're going to use. Let's consider this to be level 0. There are no derivatives involved, and all we require is that the polynomial at C is equal to the function at C, and in this case C is 0. Now, if that's the only characteristic, the only aspect of the the function and the polynomial, they're equal, you could have the function going like this, and then the polynomial just touches at that point at x equals 0. And this red graph would not match the green graph very well. So then we say, well, in addition to the function values being equal, we'll make sure that the slopes are equal. So the slope of f here looks like it's 0. So if we just require that the polynomial has the same slope of 0, then it's going to be, it has to have the same slope as the green line, but maybe it'll curve down, maybe it'll curve up. We just need to force it to have more similar characteristics, and then we go to level 2, the second derivative. So now we want the curvature of the polynomial at 0 to be the same as the curvature of the function at 0, and that would force the red graph to curve up, and now the red graph is following the green graph a little more closely than it did up here. And then we just keep on going with higher order derivatives, and we're going to force the red graph to follow the green graph. That's a summary of the strategy we're going to use, or that is used. So, how do we represent the polynomial? So, a polynomial. Well, a polynomial could be, that's a polynomial. We could have any numbers in front. I'm just making up polynomials so that we're in the right, we have the right perspective on what we're looking at. We could have a higher degree, different coefficients. All of these polynomials have different graphs. We would need to choose one polynomial that matches the graph of f closely. So now we need to generalize all these different numbers, and we could say that we'll have some coefficient times x cubed plus another coefficient times x squared, another coefficient times x, plus the constant. And I'll just put a 0 as the constant. You could say x to the 0. We won't write that. So now we're generalizing the coefficients, and if we choose the correct coefficients, then it's going to have the desired shape. So now let's talk about the first degree polynomial would be a constant plus a linear term. If we wanted to make a second degree polynomial, it would be a constant plus a linear term plus a quadratic term. And we could just make these polynomials with whatever degree we want to go to. And the higher the degree, the more closely the polynomial will follow the graph of the function. We saw that up here. As we get to higher degree polynomials, we'll get the red graph follows the green graph more closely. We just haven't made a connection yet between derivatives and exponents, but we'll see that next. And then we could represent an nth degree polynomial as so all we have to say is we have up to x to the n, and we just have different coefficients. All we have to do is find the right coefficients, and then we'll have a good approximation of the function. All right, so if we have the nth degree polynomial, it would look like this. And we need to make sure that the derivatives of the polynomial match the derivatives of the function. And that's how we're going to solve for the coefficients. So if we take the derivative of this polynomial, that's a constant, so that's gone. Its derivative is 0. The derivative of this is just a1. And the derivative here is 2 times a2x. This will be 3 a3x squared, 4 a4x cubed, and this would be n anx to the n minus 1. We're doing the power rule on all the terms. Let's find the second derivative of the polynomial. The derivative of this will be 2a2. The derivative of this is 0. Here we're going to get instead of writing 6, let's write 3 times 2a3x, 2 times 3. I just wrote 3 times 2. Here we're going to have 4 times 3, 4 times 3a4x squared. Here we're going to have n minus 1 anx to the n minus 2. We could do the third derivative. The derivative of that is 0. The derivative here is 3 times 2 a3. This is going to be multiplied by 2, and so now we have 4 times 3 times 2 a4x, all the way out to the derivative of that. We can go to the fourth derivative. Let's do the fourth derivative, just so we can see what's happening. The derivative of this is 0, and the derivative here is 4 times 3 times 2 a4. All right. We want all of these derivatives to be equal to the derivatives of the function like we saw here. Our goal is to set them equal, so let's just set them equal. And that means that we want f of 0 to equal Pn of 0, and Pn of 0 would be, here's the nth degree polynomial. We want to see what it equals when we put a 0 in for everything. So that's going to be a0 plus 0 plus 0 plus 0, because we're putting a 0 in there. And then let's say that the derivative of f at 0 has to be equal to the derivative of p at 0, and the derivative of p is a1 plus, and if we substitute a 0 in for all the x's, they're all gone, and we just have plus 0. Let's set the second derivatives equal, and we know that the second derivative is 2a2 plus 0 plus 0 plus 0. Let's set the third derivatives equal, and that's going to be, here's the third derivative of the polynomial, 3 times 2a3 plus, and then set the x equal to 0, so then we get plus 0. All right. Now, the function is equal to the polynomial, and the polynomial is equal to a0. So now we say the function is equal to a0. The function at 0 is the first coefficient. The derivative of the function at 0 is equal to the second coefficient. The second derivative at 0, the second derivative of the function at 0 is equal to the third coefficient. The third derivative of the function is the same as the fourth coefficient. Our goal was to find all the coefficients, and now we have formulas for the coefficients. We're going to have formulas for the coefficients using the function. We know the function, but we don't know the polynomial. We are creating a polynomial using the function, and here are the formulas. But we know what the first coefficient is, or the constant term is f of 0. And then we do this. We know that a1 equals f prime of 0. We know that a2 equals f double prime of 0. And we know that a3 equals f triple prime of 0 divided by 3 times 2 times 1 is 3 factorial. 3 times 2 times 1 equals 3 factorial. So here we see, due to the repeated derivatives, the repeated power rules up here, we have 3 times 2 times 1. I didn't write the 1, but there could be a 1 there, and now you see 3 factorial. 4 times 3 times 2 times 1. There's 4 factorial, and we see factorials appearing. And we can include those in these formulas. 2 is the same as 2 factorial. 1 is the same as 1 factorial, and we could even say that we're going to have f of 0 over 0 factorial. You don't have to do it that way, but look at how we get the generalization. We can make a formula for that. All right, so we have formulas for the coefficients. And now we can say, instead of writing a polynomial like this with a's, we can replace each a with something in terms of f, because we'll know what f is. So the polynomial evaluated at x is equal to, I'm just copying it from here, the nth degree polynomial at x starts with a0, but we know that a0 is going to be f of 0 over 0 factorial, f of 0 over 0 factorial times x, not times x. There's no x there, so we just say f of 0 over 0 factorial. Okay, then we're going to do a1. we need to do a1 times x. So I look over here for a1. a1 is f prime of 0 over 1 factorial. F prime of 0 over 1 factorial times x. F double prime of 0 over 2 factorial x squared. F triple prime of 0 over 3 factorial x cubed. So I'm just copying those, and you can just see the pattern. You could keep going. F to the 4th derivative of 0 divided by 4 factorial x to the 4th. F to the nth derivative over n factorial x to the nth power. And this is called a Maclaurin. If we just go to some finite degree, that's a Maclaurin polynomial, and we can use it to approximate functions, and the further we go, the more accurate it'll be. All right, and so here's what the question would look like. We need a 4th degree polynomial, so that means we are looking for a polynomial that goes like this. It's centered at 0. We want f of 0, f prime at 0 over 1 times x, f double prime of 0 over 2 factorial x squared, 3rd derivative at 0 over 3 factorial x cubed, 4th derivative at 0 over 4 factorial x to the 4th. That's the 4th degree polynomial. So now we just need to find everything to substitute, which is just really the function values and their derivatives. We have to go all the way to the 4th derivative. So let's make a table for that. We have, we want f of 0, f prime at 0, so f is e to the x, and we want e to the 0. The derivative of e to the x is e to the x, so this is going to be a pretty simple one. Remember that if y equals e to the x, y prime equals e to the x. We're doing higher order derivatives, but it's just always going to be e to the x. So now we know what to substitute, and we're going to have, I should change this n to a 4. So that's a 4. P4 of x is f of 0. Well, that's 1. This will be 1 over 1. This is 1 over 2. So let's write x squared over 2 factorial, x cubed over 3 factorial, all right, and if we graph this, it will curve closely to this for a certain interval. Let's stay with the fourth degree. All right, do the same thing with that. Make sure you just find the derivatives of cosine. Pause the video and try that. So we have f of x is cosine, f prime is negative sine, and then we have to do the derivative of that, so we get negative cosine, and then we're going to do the derivative of that would be sine, and we'll do the fourth derivative. The derivative of that is cosine. Then we evaluate it when x equals 0. So we have when x equals 0, cosine is 1. Sine is 0. Cosine is 1, but we'll have a negative there. Sine is 0. Cosine is 1. So here with the fourth degree polynomial, we have f of 0 plus the derivative at 0, second derivative, third derivative, and fourth derivative. Then we substitute f of 0. F of 0 is 1. Here we're going to go f prime of 0 is 0. So that is just going to be 0x. F double prime of 0 is negative 1. And here we have the third derivative at 0 is 0. 0x cubed. And the fourth derivative is 1. So we can say that the fourth degree Maclaurin polynomial for cosine is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. And that's the end of this video.